In 1977, the Voyager probes began their journey into deep space. Mounted to their hulls were these etched greetings, the golden records designed to represent humanity to any civilization they might eventually encounter. Despite the ambition, the mission was directionless. Voyager had no specific star system as a destination. It was a passive release of information into a void so vast that the chances of interception were nearly zero. At the time astronomers focused their search closer to home, we sent probes to our immediate neighbors Venus and Mars, expecting to find environments that mirrored the biological diversity of Earth. Those missions returned images of a graveyard instead of vibrant ecosystems. We found rocky surfaces that had been scorched and sterilized by solar radiation for billions of years. The emptiness of our own solar system forced a change in strategy. To find a living world, we had to look beyond our immediate neighbors and into the deep reaches of the Milky Way. The difficulty lies in the light stars are billions of times brighter than the planets orbiting them, effectively drowning out any small dark objects in their immediate vicinity. Early attempts to physically block out starlight through direct imaging proved unreliable. The glare is so intense that telescopes frequently miss smaller Earth-sized planets or those orbiting at great distances from their sun. Finding these hidden worlds required a move away from traditional photography. Scientists had to develop indirect methods detecting the presence of a planet by measuring its physical effect on its host star. The first primary method is radial velocity. Even though a star is massive, an orbiting planet exerts a constant gravitational tug on it, forcing the star to move in a tiny measurable circle. We detect this movement through the Doppler effect. When the star's wobble brings it towards Earth, its light wavelengths shorten and shift toward blue as it moves away. They stretch and shift toward red, while the wobble method confirmed hundreds of planets a second technique. The transit method has become our most successful tool for mapping the galaxy. This relies on simple geometry. When a planet's orbit carries it directly between its star and our telescopes, the star's observed brightness drops by a tiny specific percentage. Measuring that shadow reveals the planet's physical properties. The deeper the dip, the larger the planet. The longer the duration of the dip, the slower its orbit. Tracking these microscopic changes in starlight, astronomers have confirmed the existence of nearly 5,000 exoplanets, turning the search for a second Earth into a data-driven science to find life. We filter this data for the habitable zone, the specific region around a star where temperatures allow water to exist as a liquid rather than boiling away or freezing.